Well, I was talking about that minus a point. That is disconnected, right? I mean, you have two disjoint open subsets that cover the whole thing, right? So, I mean, somehow, obviously, like, you shouldn't put too much faith in pictures like this, but in this case, it's actually accurate. You can really think about the points over C. This is reducible but connected. And if I delete this point, it's now disconnected. This is an open set, and this is an open set. And if I had this point here, I wouldn't be able to sort of fix it, to keep them both open and add in this point somewhere. But if I remove this point, then these two open sets cover everything. And it's maybe worth mentioning, right? Like, the reason you should be a little bit careful about this is, oh, well, for example, there are points corresponding to other prime ideals. So there's a generic point for the x-axis, and there's a generic point for the y-axis, but those are contained in these two open sets. So even when I sort of think about the scheme, so this is, removing this point makes it spec of C of xy mod x times y, but now by removing this point, I'm localizing at a function that vanishes only at that point. I shouldn't actually put parentheses there because I'm not localizing at this maximal idea. I'm localizing by adding in the inverse of x plus y. And the way that manifests algebraically is this localization is not a domain. Or it's even worse than that. It's the direct sum of two rings. This is isomorphic to the direct sum of Laurent polynomials in X plus Laurent polynomials in Y. Right? And I mean, this is sort of a weird thing, but like, here there's an element 1, and that's X divided by X plus Y. And here there's an element 1, and that's Y divided by X plus Y. All right, so like if I wanted to define the isomorphism here, I would take a polynomial in X and I would multiply it by this guy, take a polynomial in Y and multiply it by this guy, and that gives me an element of this localization. All right, cool. Uh-huh. Oh, sorry, yeah, I wasn't being very careful about my notation here, right? This is an isomorphism of rings. And the way that manifests on the level of geometry is if I take spec of this guy and remove the one point where this vanishes, it becomes the disjoint union of two copies of spec of these rings, right? So the y-axis here is spec of this ring, the y-axis minus a point, and the x-axis minus a point is spec of this ring. Feel like I haven't actually mentioned this notation yet to make this easier. For any commutative ring, an sub k means spec of polynomials in n variables over k. So this is a1 minus a point. This is a1 minus a point. And if I just looked at spec of this guy, this would be two copies of a1 glued at a point. All right, great. So that was kind of a preamble to class. Are there any other questions? If the ring is a direct sum or direct product, yes. You're going to prove that on your homework. All right, cool. And you'll see why on your homework. There are various other ways of seeing why, right? Like, I mean, what's happening here? I have a ring that's a direct sum. So I have two elements, which are the identity in one of the rings, the identity in the other one of the rings, which, is sort of going to it gives me a function that's one somewhere and zero somewhere else. And that sort of gives you the disconnection. All right, cool. So I wanted to finish up a little bit talking about affine schemes, because I just kind of ran out of time. So there's this example, which you might recognize as being the image on the course website. It's trying to draw a picture of what spec of Z adjoint T looks like. So this is the set of all prime ideals in ZT. So what do such prime ideals look like? Well, one good way of coming up with such a prime ideal is to just take a prime in Z. And I'm going to represent those by vertical lines. You might ask, why would I didn't draw them as lines? It's because when I mod out by this prime, I get something of Kroll dimension 1. This whole ring has Kroll dimension 2, so it's going to be a surface type thing. When I mod out by this prime ideal, I get polynomials in FP. So that's a polynomial ring over field that has Kroll dimension 1. It's PID. So, this is the prime 2, this is the prime 3, this is the prime 4. Right? And then I'm going to have, so these are sort of somehow arithmetic, and then I'm going to have some more geometric things. Yes. Oh, yes, 4 should be a 5. Yes. Sorry. That's a very, very good point. Um, you know, uh, part of the lore of algebraic geometry is using things that aren't really prime numbers because you aren't thinking about what you're doing. There's sort of a very famous story about Grothendieck giving a long talk where he was talking about some prime p, and Zariski in the audience hassling him about like, what prime do you want to use? And he's like, oh, I don't know, it's just some prime. And Zariski like, well, like what prime? And Grothendieck's like, you want me to pick an actual prime number? Okay, fine, 57. Which, yeah, is now sometimes facetiously referred to as the Grothendieck prime. All right, anyways, yes. I'm also going to have ideals that come from looking at like T, right? And if I mod out by T, I get Z. So that again has Kroll dimension 1. So I should draw this as a line as well. And it's kind of perpendicular to these lines, which, I mean, it sounds slightly insane, but think about C adjoin 2 variables, right? Then setting X to 0 and Y to 0 give you orthogonal lines. But what if I instead look at something like T squared plus 1, right? That's a perfectly good prime ideal. It doesn't factor over the integers. Well, that sort of looks like I have sort of a line, but it's going to have some intersection points here. Here, there's sort of a failure to have an intersection point. And here I get a sort of tangency. So this is the ideal T plus 1. So mod 2, this is equal to T plus 1 squared. So the fact that I get a square tells me I have a kind of tangency here, something where I have a higher order point of intersection. And then, did I do this picture right? Yeah, I thought I did. Oh, right. Yeah. So mod 3 minus 1 is in a square. So there's no sort of solution to this mod 3. And so I should sort of say more specifically, this intersection point, this is the ideal T2 comma T. This is the ideal 2 comma T plus 1. Right? And here, well, I can look at 3 T squared plus 1. So there's sort of no solution to this over F3, and that's manifested in this being a prime ideal, or maximal ideal. On the other hand, here I have 5 T plus 2, and here's 5 T minus 2, because minus 1 is a square mod 5. Yeah. Well, it's sort of, right, the way to think about this is, right, when I was looking at polynomials over R, I have points that correspond to complex points, yes. Points over field extensions. So this corresponds to a solution to this equation over a field extension of F3, not over F3 itself. Yeah. So I mean, there sort of is a point of intersection here, but it's kind of a thick one that somehow corresponds to a field extension. And actually, what I mean by that is one of the things I want to make a little more precise. So one thing I don't think I said at the end of class yesterday that's very important. Mm-hmm. Well, I looked at solutions to T squared plus 1 mod 5. So here I had T squared plus 1 factors this way, mod 5. T squared plus 1 is congruent to T plus 2, T minus 2, mod 5. This is just that 2 and 3 are the square roots of minus 1 at mod 5. All right. So theorem, because I don't think I said this last time, if I take spec of R and look at the point in here corresponding to a prime ideal, of course, one of the things I'll want to look at is this structure sheaf, and then look at the stalk at this prime. And I think I have mentioned this before, but let me just make sure I have it down as a theorem. This is the local ideal FP. Right, so let me just say, why is that? Well, every element here is represented by a germ. It's represented by some s in the sections of O of x. Well, I could say I'm an open set, but I can always shrink that open set to be a distinguished open. So in some df, where P is in df. So what does it mean that P is in df? That means F is not an element of P. Okay, well, that exactly says that S is equal to some R divided by R prime, or sorry, R divided by F to the N, where F to the N is not in P. And that's just saying that this is an element of the localization at P. All right. Cool. So this tells us that the spectrum of a ring is not just a ring space. It has an extra property. It's a locally ringed space. A locally ringed space. This is one of these definitions that sounds very dumb when you say it. Is a ring space such that the stalk of the structure sheaf, which is often called the local ring at P, is a local ring. As I think we did discuss, the name local ring exactly comes from this origin. You know, people didn't say it quite in terms of schemes, But it comes from the idea that it's about thinking about what happens locally around that prime. So this just tells us spec R isn't just a ring space, it's a locally ring space. So one of the nice features of a locally ringed space is, of course, a local ring has a unique field, which is its quotient. So any local ring has a residue field, which is just if my local ring is R, that's R mod its unique maximal ideal. So in particular for RP, this is the fraction field, and I'm going to copy Vacchio's notation here. He writes K of R mod P. Right? I invert all the stuff that isn't in P. So when I mod out by P, that just means I've inverted everything and I've taken the fraction field. All right. So for example, here, what happens? Well, when I take one of these kind of lines, then I get something I would recognize as a function field, right? Here's rational functions in F2, F3, 5. Here I'm getting Q. Here I'm getting, so if I look at this intersection point, then I get F2, F2. Here I get F9, right? There's also the point 3 comma x plus 1. And this is 3 comma x, 3 comma t, sorry, not x. These have residue field F3. So this residue field for points is kind of measuring something about sort of the size of the point, right? In the scheme world, points aren't just points, they also have some extra schemey information on them, which you can think of as this residue field. For example, here I'm going to get Q adjoin I. And this is really only telling you sort of part of the story, right? As we discussed, if I take this whole closed subset, that's actually spec of F2 polynomials in F2. And what I'm telling you here is like, if I look at the generic point of that closed subset, I get this field as the fraction field of F2 of t. And similarly, this line is a copy of spec Z. This line is a copy of spec of Z adjoin I, the Gaussian integers. Right, so exactly what I'm seeing here is over 3 and 5 split as Gaussian primes. Sorry, 2 and 5 split as Gaussian primes, 3 doesn't. And so I get this F9. That's the unique quotient of Z adjoin I, which is field of characteristic 3. All right, cool. Are there any questions? Okay, one more point that's worth discussing. And this is one of these things that I suspect we'll keep coming back to. Oh, yeah. Sorry, what, 0? Oh, 0. I mean, 0 is sort of, it's the whole space, right? If I took the fraction field there, I would get rational functions in Q. All right, cool. So the one thing I kind of haven't dealt with here, or at least I only dealt with it a little bit here and kind of swept it under the rug, is what about nilpotents? So we've sort of hopefully gotten a little bit comfortable with the idea that there's not just one point in scheme world. There's a different point for each field that might be sitting on that point. But then there's another kind of structure that points can have, which is they can have some nilpotent stuff on them. I could have something like C of t adjoining t squared. Or for example, here, right, if I applied both of these ideals, if I look at z of t mod t squared plus 1 and 2, that's isomorphic to f2t mod, I'll write t plus 1 squared. Right? So again, this is sort of, these are guys which are kind of, they're somehow a slightly different point than if I just put the field there. Right? There's a point that has f3 or f2 sitting on it. And there's a point that has this guy. And as ringed spaces, they're different. Right? This is just kind of dumb. I could take any ring and define the one point space to be a ringed space, where on the unique non-empty open subset, I put that ring. All right. But how do I think about this geometrically? So geometrically, the way you should think about this is the points are the same, but they're a little bit thicker. So you would often sort of draw this as not just a point, but like a point with a little bit of fuzz on it. And well, like I said, it'll be kind of a long-term project understanding what this means, right? Kind of what this means is I have a point and I remember just enough of a neighborhood to not just remember the value of a function at this point, but to remember its derivative, but not its second derivative or its third derivative. Only I have just enough to remember its first derivative. Of course, I could make my fuzz a little bit thicker, and I could also remember the second derivative. I still don't have any other points. It's one point, but it just gets sort of a little bit fatter and sees a little bit more of what's going on around. And this is actually a really natural thing to do, as exactly this thing sort of demonstrates, right? That when I say something like, oh, I always have two square roots of a given number mod p, if there are any. Well, you've encountered this idea all your life of like, oh, well, this one, there's only one square root, but you have to somehow count it twice. And this is one way of saying what that counting it twice means. It's that I don't just get the point with f2 on it. I get that guy, but a little bit thicker. And that little bit thicker counts for the second square root. Uh, and of course, once we go into higher dimensions, there are lots of other possibilities. For example, I can take C of xy mod y squared xy. But what does that do? Well, if I looked at closed points, if I looked for x and y that actually satisfied this equation, of course, I would have to have y equals 0. And if I invert x, then this just becomes y equals 0. But at the point where x equals 0, something a little bit funny happens. I have a little bit of a thickening there. I exactly remember what the derivative vertically along the x-axis is at that one point and nowhere else. So this is the kind of funny stuff that can happen with schemes. But even if you only originally wanted to think about things where you didn't have this fuzziness, you intersect them and the fuzziness is kind of forced on you. Yeah.
So
I mean, you could call it length of the module. Um, so I mean, in this specific case of things intersecting, you can interpret, it's what people usually call multiplicity. Um, so, I mean, somehow I would say this is like how people usually define multiplicity. But I'm just trying to bring up a context where you've encountered this before, right? A very similar thing is I could be looking at C of xy and look at this mod two polynomials. So what does that mean? That means I'm taking f equals 0 and g equals 0, and I'm intersecting them, right? And Bezout's theorem tells you how many intersection points you should expect. And, well, an important part of Bezout's theorem is you have to count intersection points with multiplicity. And in this case, it's very literally that intersection point. If I look at a little neighborhood here, I'll see a copy of CT mod t to the n for some n. Right? So if I take that intersection as schemes, if I think about this quotient as defining a scheme, then multiplicity is saying, oh, on this intersection point, I don't just get a copy of C, I get a copy of this sort of slightly bigger nilpotent local ring. Yeah.
So,
Well, if you do it in the affine setting, it's an upper bound.
Yeah.
I mean, we'll talk about projective space soon. You maybe won't have too much time for it, but I just thought it would be bad to completely skip discussing nilpotents because they're very weird, but very important. It's sort of one of the reasons that we want to start thinking about schemes is to kind of deal with nilpotents correctly. Okay. But indeed, you said, oh, we should think about projective space. And indeed we should. But projective space is kind of one of the first examples of, well, one of these things we're eventually going to call schemes, which is not an affine scheme. It's not spec of a ring. So we need a little bit of terminology to be able to talk about things that aren't spec of a ring. Okay. So, sorry, I do these in the right order. Oh, kind of weird. Okay, yeah. I just went past the first definition one. So we talked about ring spaces. Okay. We should talk about what it means for ring spaces to be isomorphic. Note, I'm not discussing general morphisms. It's often easier to talk about isomorphisms first. So an isomorphism of ringed spaces. So my ring spaces are x, O of x, and y, O of y, is a homeomorphism of the underlying topological spaces. That makes sense. So we know that we should want their underlying topological spaces to be isomorphic. But then we have to also say that somehow these sheaves of rings are the same. And we have to be careful about that because O of x and O of y, they're sheaves on different spaces. I can't say that those are isomorphic. But we have this operation called push forward. So an isomorphism of sheaves of rings from the push forward of O of x to O of y. So it's these two pieces of data together. And I could extend this a little bit I could talk about an open inclusion. Is an isomorphism to an open subset. So one thing we'll be using fairly often is that if I take an open subset of a ring space, that has a canonical ring space structure, where, right, an open subset of the open subset, I could just think of as an open subset of the whole space and take sections over that. And that's, for example, key for one of your homework questions, where you'll be thinking about the distinguished open subset DF as a ringed space on its own. All right. Cool. So now that I know what it means to have an isomorphism of ring spaces, now I can make this definition. An affine scheme is a ring space isomorphic to spec of R are a commutative ring. Now, this is a slightly weird definition, right? We've defined what spec R is as a ring space. And now I'm just saying, well, I might be going around in the category of ring spaces and find some other ring space that happens to be isomorphic to one of these spec Rs, but not literally the same as one. And I want to call those affine schemes. Note, if X is an affine scheme, then you can figure out what the ring is immediately. X is isomorphic to spec of the sections on the whole thing of O of X, right? We saw last time that if we take spec of R, sections on all of spec of R is R itself. So I can always, if something is an affine scheme, I can canonically produce the ring that it's spec of. So don't think this is some clever way of getting around different rings having the same spec attached to them, because that can never happen. All right. But it is useful because this lets us give a nice definition of schemes. A scheme is a ring space so the sort of nice way to say this, which is locally an affine scheme. So that means that for all elements of X, there exists an open subset containing X such that when I look at the restriction of the structure sheaf to U, so this is a special case of pullback, but which we haven't defined, but it's a very simple case, which is just if I have an open subset of U, I think of it as an open subset of X, and I take the sections over that. And if I look at U as a ring space with this structure sheaf, that's an affine scheme. All right. So we made it. We know what schemes are now. We can all go home. Oh, well, so by this definition, a scheme will always be a locally ringed space. So whether I wanted to say locally here, it doesn't matter. Because being locally ringed is a local property. It's a property about neighborhoods of every point. And so it carries over from affine schemes to schemes. And I just gave you the proof for affine schemes that they're locally ringed. So yeah, this is an important thing about schemes, right? That every point in a scheme has a local ring, has a residue field, has a field attached to it that kind of tells you how big that point is. All right, so cool. Now we know what schemes are. Well, when you make a definition like this, of course, the first thing you should address is what are some schemes that aren't affine schemes, right? The first thing you want to know when you have this definition is what kind of things could you be cooking up that you needed this more general definition of something that's locally an affine. So the first definition, first example, which is maybe not that exciting, is there are open subsets of affine schemes which are not affine. And we've talked about one example of these quite a bit. I could take A2, or more generally AN, and subtract a single closed point. And that's not an affine scheme. And I should say the reason for this, so there's a fancy categorical way to say this, which is any scheme has an affinization, an initial scheme that it maps to, which is affine, which just means if I have any scheme, right, there's a natural map to, well, I haven't defined morphisms of schemes, so let's not take this too seriously, but I can always look at spec of functions on it. And if this is an affine scheme, this had better induce an isomorphism on the underlying topological spaces, right? Let's not worry about too much what happens when this isn't an isomorphism. But if I'd started with an affine scheme, I have to get a bijection here. So that's what's wrong here. If I call this my X, then we already calculated that the sections on this are exactly, oh, sorry, I should call this K of XY, right? But I don't get a bijection of this guy to spec of this ring. I get an open inclusion that misses one of the points. So this is not affine. And in general, if you take an affine scheme and just start pulling random stuff out, you almost certainly won't get something affine. If you do something other than pulling out the zeros of a single function, you should expect that what you get probably won't be affine. It's not quite literally true that never happens, but somehow it's some sort of weird coincidence if it does. All right, but that's not that satisfying, right? It's not worth making this definition to only talk about open subsets of affine schemes. Yes.
There's the inclusion of schemes.
I think that's what I just told you. I have to think about whether it's left or right, but
If it's the same as
no, it's comes into this. So I think that's a right edge to inclusion of we'll worry about it later. Right, I leave that as an exercise to figure out what. I mean, we haven't talked about schemes as a category yet, so it doesn't really make sense to start talking about functors, but it's also not that hard to figure out what's going on here. Okay. So what else can you do? Well, there's one sort of useful general construction, which we'll talk about the easiest case of right now, which is I could take two schemes. Let's say they're affine, but they don't have to be. And I can take open subsets of them. And I can take an isomorphism of ring spaces between these two open subsets. right? And there's a natural construction of a topological space where I glue the underlying topological spaces X and Y on this open subset. So if you're going to think about this as sort of a categorical thing, the thing you're going to do is here I have U and V. So I think of this as sort of one space. It maps into X, it maps into Y. And there's a unique topological space that makes this work, which is just I take X disjoint union Y, and then I mod out that if P of X equals Y, then I identify the 2 points X and Y. So if you want to be fancy, this is a coproduct in the category, not a, sorry, a push out in the category of topological spaces, but it's also just like literally do this identification with this equivalence relation. And I just equip this guy with the quotient topology from X disjoint union Y. So something here is open if its pre-image in X disjoint union Y is open. All right, this is a perfectly good topological space. And there's just kind of an obvious way to extend the structure sheets. So just for convenience, let me call this guy Z. And if I want to know what sections of Z are, O of Z are on some open subset W, well, I should look at a section over X intersect W and over Y intersect W. And then I need compatibility on the overlap, right? So this is basically just saying, oh, well, I need to have this gluing property for sheaves. I think you probably could state this all in terms of a sheafification, but let me just kind of write it out explicitly such that if I take half and I restrict it to U intersect W, I take G and I intersect that to V intersect W. Well, I don't want these to be literally isomorphic, but there's an isomorphism between the restriction of these structure sheaves to U and V. So there's an isomorphism, which should send this restriction of F to the restriction of G. And again, this is just kind of automatic from the sheaf gluing property. I think probably you could define a pre-sheaf that was something like, it's an open subset that's contained in X, it's the sections on O of X, and one that's contained in Y, it's these sections in Y, and then you sheafify. It would just tell you to do this construction. Okay, so that's a general recipe. What kinds of situations do we want to apply this in? I mean that, so this lives in O of X, U intersect W. This lives in O of Y, U intersect, sorry, V intersect W. There's an isomorphism from U to V, and that identifies these two open sets. And then there's an isomorphism between the push forward of the structure sheaf and this guy. So these two spaces are isomorphic. And I mean that this guy is sent to this guy under that isomorphism. All right. So one obvious example is I could take X to be A1K, Y to be A1K, U to be, to avoid confusion, I'll use two different variables. So this is spec of C adjoint X, this is spec of C adjoin Y. And so I'm going to take U equals D of F. So the point away from the origin, B is equal to D of Y. All right. So one thing I could do is, I've taken A1, I've subtracted a point, I've taken A1, I've subtracted a point. I could identify those in the obvious way. So I could take my phi from U to W, U to B, to just send X to Y. And the relevant thing here is I get an isomorphism between Laurent polynomials in X to the functions on this U to Laurent polynomials on Y. All right, so what do I get here? The space I get is the affine line with the origin doubled. And pretty much everything else the same. In particular, there's one generic point for the whole space because this isomorphism identifies the zero ideals in these guys. Right? The generic point corresponds to the zero ideal here and the zero ideal here. Since I'm low on time, I won't say a lot about this guy. What you can figure out is if I want functions on an open set here, an open set, well, there's the empty set, but let's not worry about that, is the complement of finitely many points. So I can remove finitely many points from the rest of this, and I can remove one or both of these origins if I want to. And what I'm going to get is polynomials where I invert those whose zeros are outside the points I removed. And if I have a zero at the origin, I have to have removed both copies of the origin. So somehow you see surprisingly little about the actual functions on here. It doesn't really change that much. But this is a perfectly fine scheme. All its dues are paid, but it's a weird one. So generally, we'll want to avoid situations like this, but we have to know it's possible to know what we're avoiding. So this is kind of the scheme version of being non-Hausdorff, right? The actual topological space is never Hausdorff, but affine schemes sort of behave like Hausdorff topological spaces, and this one does not. All right, a more interesting one is instead I could take phi prime from U to V to send X to Y inverse. Now this is a perfectly good isomorphism between these Laurent polynomial rings. Right? So now I'm sending f of X to f of Y inverse, and that's okay. So what's happening now? Instead of getting a doubled origin, now I have sort of one of my guys like this, and one of my guys like this. And so exactly what I'm doing is I'm adding a point at infinity, right? From the perspective of X, the origin in Y becomes a point at infinity, right? If Y is 0, then X is infinity, and if X is infinity, and Y is 0. Okay, I just said the same thing twice. So this is T1. Okay. And I'll note here, I'm not having to do this over C. I think I wrote C here, but I was trying to do this over an arbitrary base ring, and then I failed. So sometimes I'll use C just to be comforting, but actually this makes sense over any ring. So I can think about P1 over Z this way. That's a perfectly good scheme. And it's kind of weird. It's going to be like that spec of ZT picture I had before. But now on every one of my horizontal lines, I've added in a point of infinity. commutative ring. There's nothing special about fields here, right? I have an isomorphism between these rings. That's all I need to do. All right. Any questions? Yeah.
You look at shit like
Right, but that's a pullback in the category of schemes. So that's a fiber product, and we'll talk about that later. Right, I mean, this isn't something you can interpret necessarily in the category of rings. That's the point, right? These guys are not affine schemes. There's no ring. I mean, it's a little bit of a lie in this case because there's a different way of turning rings into projective schemes. But there's no ring where I can apply spec to that ring and get these guys. They're not affine schemes. I can't think about this construction as construction purely happening in the category of rings. If you wanted to, you could think about it in the category of functors from rings to sets. Right? You could phrase this all in terms of the functor points, but not just like trying to construct some new ring.
I mean,
Yes, but then you can do things that make objects that don't come from that functor. All right, I'm out of time, and the next guy in this classroom is always yelling at me and not having the board clean, so I'm going to try to stop on time.